Okay, we are going to start a walkthrough of a horizontally fired projectile. And this is example 3.6 in your textbooks. Basically, we could see we have a person on a motorcycle that goes off a cliff. Now, for ease, I'm not going to draw a motorcycle. We'll just draw it as an object fired off horizontally, which means as soon as it takes off, he starts going down. Something like that. You could refer to the specifics of the diagram in your book. But what we have going on here is, first, because of what we learned in class of the independence of the horizontal and vertical components, we are going to list all the givens horizontally and all the givens vertically. So we are told that this thing is traveling at a horizontal 9 meters per second as it's on the horizontal surface up here. What's going to be in question is some factors when t equals 0.50 seconds. And one thing we always have to say, as long as it's fired horizontally, is that initial y velocity is 0. It's essentially, vertically speaking, like it's being dropped. And if we're ignoring air resistance, it's also like it's in free fall. And again, the only really piece of crossover information between x and y is going to be t, because everything's happening at the same time. And unless told otherwise, the initial position, both x and y, when it leaves the table, is set at 0. So the first thing this goes on to ask me for is find the position x and y at time t equals 0.5. And what we could go to for our x equation, well, it's pretty simple. Since horizontally it will be traveling at constant velocity the whole entire way through that trip, the whole way through this trajectory, as long as air resistance is negligible, it will travel at the 9 meters per second we listed before. And so we simply just use essentially v equals d over t, but in its specified form for x to stress that we're on the x position here. So 9 times 0.5 is 4.5 meters. Out this way to the right he will be. And while he's moving that way, he's also moving downward. And we could go to one of our free fall equations that's just tweaked now with y components. And since Vy initial was 0, one of our 4 free fall equations just turns into 1/2 gt squared, which means he goes down a negative 1.2 meters during that 0.5 seconds from when he left the edge. So we can see here, this is y, this is x, and so there's now a resulting position that he is away, or a resulting distance from where he left. And they go on next to ask me what that is, and if we have the two components at time t equals 0.5, then we simply plug them into the Pythagorean theorem to find the distance. Since it says distance, right now we don't want the direction, just the magnitude of that vector, of that position vector, 4.7 meters after plugging it in. Moving on, we want the velocity after, and oops, there's a little mistake here, that should read 0.50 seconds. We'll have to fix that later. The velocity at this. Now, like I said before, horizontally you don't change till you hit the ground. So there's no calculation necessary. Vx is 9 the whole way through. Y will change because gravity is pulling on it, Vy will. And we use, again, one of the free fall equations with Vy initial set as 0 because it's a horizontal projectile. Plugging into that, we get negative 4.9 meters per second. So we have, these are their two individual components on the x and y, and we could plug them into the Pythagorean theorem to find out their resulting velocity, similar to how we did it up there. This one also wants us to find the direction, and like we always do now, we're beneath the horizontal. So theta is going to be this angle in the southeast quadrant, and we just perform the tangent theta inverse operation, and we could express it as 29 degrees southeast, we could express it as negative 29 degrees, or from as a terminal angle as 331 degrees. Either one of those 3 is fine. We'll know what you're talking about. And that's a pretty basic problem dealing with horizontally fired projectiles.